Okay, so I think we can get started. So last lecture we introduced analysis of variance, which is ANOVA. And like we said, ANOVA is really used for when you have more than three groups and you would like to compare the population mean difference among the different groups. And we started a little bit on the chi-square test or categorical data last lecture. Today, I was hoping that we can finish this lecture and we can also finish the non-parametric work or the non-parametric test. And for that, the reason for that is then we will have the remaining two lectures that devoted to regression, because regression is really important topic and typically we spend more than one lecture on that. So let's see if how much we can finish today. So last time for categorical data, we introduced what is a definition of a contingency table, and we gave you a couple of examples. So contingency tables are really used to display the interactions or the different categorical data and how they combine together. So if you have a 2x2 table, then you have two variables and each variable would be a categorical data, and by 2x2 we mean each variable has two levels. However, contingency table can also used be in the more general situation where you have more than two categories. If you have more than two variables, you need to have multidimensional contingency table. And then we started to introduce a chi-square test, because chi-square test is really used whenever you have a contingency table. Most likely the choice to make a statistical inference or statistical test is chi-square test. And chi-square test, you probably have heard that quite often because it is very frequently used in statistics. And so we want to introduce what is chi-square test for. So chi-square test is really for testing the dependence between the rows and the columns in a contingency table. So what we mean by dependence is really mean whether this column variable is independent of the row variable. And if you think that in mathematical language or statistical language, when we see that the row variable is independent of the column variable, we really mean that the proportion of each row is equal to the proportion, is equal to, according to different columns of the column variables. So in this example, if we are looking at gender, the first variable, which is on the row, and also hand preference, the second variable on the column, if we are asking the scientific question that whether gender is independent of hand preference, so in mathematics or in statistics, you can translate that into the proportion of female that is left-handed is the same with the proportion of male of female that is right-handed. So essentially you're looking for this proportion, whether this two proportion is the same. And then the alternative hypothesis is naturally they are not the same, because if they are not the same, that means if for some reason that female is more likely to be left-handed than male, so in that way that proportion would be different, and then that means scientifically it means that gender and hand preference is dependent. So to test that hypothesis, chi-square test is a typically used test that to answer that question. And chi-square test have this formula, and when you see this formula, essentially it has two numbers, the expected and the observed. O stands for the observed and E stands for the expected. And so that means to perform a chi-square test, you need to calculate two tables. One is the observed frequency, and then the other one is expected frequency. The observed frequency, you actually do not need to do any work on that because it's given. So now we are going to talk about how you're going to calculate the expected frequency. So remember, when we talk about hypothesis testing, most of the calculation, or almost all the calculation actually for hypothesis testing, it's always under the null hypothesis. It's always under when the null hold, what is your expected frequency or what is your expected distribution. So for this time, when we talk about expected frequency, it's essentially what we mean is expected frequency under the null. So if you think about it, if under the null, it means that hand preference and gender is totally independent. So in that way, it doesn't matter whether you are a female or you are male. The p hat, which is the proportion of the left-handed, should be the same for female or male. So in that way, you can actually, because we have 120 females and 180 males, so in that way, if they are all the same under the null hypothesis, if their proportion are all the same, we can pull the data together, which means the denominator now can be pulled together by 120 females plus 180 males. So you have 300 total samples in total. And then among those 300 samples, how many of those are left-handed? You have 12 out of the females and you have 24 out of the males. So among those 300 total samples, you have 12 plus 24, which is 36. And those are the left-handed individuals in your samples. So if you ignore the gender difference, which basically means if you accept the null hypothesis that there's no gender difference in terms of their hand preference, proportion, or probability, essentially you can pull the data together and you can put all the left-hand side individuals over the total sample size, and that gives you a p-hat estimate. So that is 36 over 300 is 0.12. On the other hand, if you think the similar way, the proportion of right-hand side in all your sample under the null hypothesis should be 1 minus this p-hat, or should be, or you can calculate that it's 108 plus 156, this summation, which is 264 over 300. So essentially, if you look at in the chi-square test, this proportion is calculated by this column total over the grand total. So that gives you the p-hat that corresponding to each column. So after you have this p-hat, essentially it means that you can populate an expected frequency table under this p-hat, which is calculated under the null hypothesis. So if you think about it, then if you have 120 females in your sample, and under that p-hat, which is 12% right here, so that means there's no difference for gender, for female and male to be left-hand side. As long as it is a sample in your population, the proportion to be left-hand side should be 12%. So then how do you calculate the expected count? That should be equals to that p-hat multiplied by the total number of females. So 12% multiplied by 120. So that gives you 14.4, which is the expected number of female who is left-handed under the null hypothesis. And then similarly, that p-hat over multiplied by 180. So that would be the expected number of left-handed in the male samples. And those two numbers, remember, those two numbers are calculated under the same p-hat. And that is because you're assuming that for female and male, their left-handed proportion is the same under the null. And similarly, you can do this 1 minus p-hat multiplied by 120, and you get this expected number of females who is right-handed, which is 105.6. And for males, you can use 1 minus p-hat multiplied by 180, and you get this expected right-handed set individuals in the males. So now you have two tables essentially. You have the observed table, which is the observed frequency, and on the other hand, under that p-hat or under the null hypothesis, you also have a table which is called expected frequency under the null. And this expected frequency doesn't have to be integer. So after you have this two table, the O and the E, to calculate a chi-square statistic, what do? You essentially, you take the squared distance between the observed and expected, and you take that squared distance and you take a summation over all the cells. So that is the numerator. So O minus E, take the square, and you do that for all the cells. So here you have 4 cells. So what do is the square distance of this cell, 12 minus 14.4, take the square, and then this one, and this one, and this one. So that gives you 4 summation. So that is the numerator. And in the denominator, you put expected frequency here. So this square distance over the corresponding expected frequency, which is 14.4 right here. So you do that for each cell, and the final chi-square statistic is the summation for over all the cells in your contingency table. So this gives you a chi-square 0.75. And what is the rationale to calculate this number in this way? It essentially tells you that under the expected, which is under the null hypothesis, if the null hypothesis is correct, you should observe numbers as your expected. So intuitively, that means if your observed number is quite different from the distribution of the expected numbers, then you have more evidence to reject the null. If your observed number or table is very close compared to the expected table frequency, in that way you have less evidence to reject the null because they are very close to the expected. So essentially, this summation tells you how different this expected table is from the observed table. And the bigger this chi-square statistic is, it gives you a metric that the bigger the difference is. So here we have a chi-square 0.75. So remember what I told you about any hypothesis testing. You need to know that the first thing, conceptually, what is the null and the alternative hypothesis? And then the second thing is what is the formula to calculate a test statistic? So now we have actually finished 2 steps. We know what is the null and the alternative hypothesis, and we know how do you calculate the chi-square test statistic. So the last step is what do you compare to? After you have a test statistic, what do you compare to get a p-value or to make a decision? So After you have this chi-square test statistic, you should compare to a chi-square distribution. So remember, we talked about chi-square distribution. There are several properties of a chi-square distribution. Chi-square distribution has one parameter, and that parameter is called degrees freedom. So whenever you talk about chi-square distribution, you need to specify what degrees freedom is that chi-square distribution. And then chi-square distribution is always positive. So it is because it is a square term, essentially. And you can see that from the way that you calculate this chi-square statistic, it is always going to be positive because it's a summation of squared distance. So chi-square is always positive. So that means for chi-square, it is always a one-sided p-value or one-sided critical region. Although your test could be two-sided, your test could see that the proportion of female and male that has left-hand side is different. It doesn't have to be that female is higher or male is higher. But your test can be one-sided, but for chi-square, it's really that it's always a two-sided test, because here, by taking that square, you essentially ignore all the directions. So you put all the alpha into this right-hand side area. So essentially, if you get this is alpha equals 0.05, and you got a critical region value which is 3.8. So what does that mean? That means your rejection region is only to one side, is to the right side. So as long as your observed chi-square is bigger than this critical value, you are able to reject the null hypothesis. And then if your observed statistic is less than this critical value, you fail to reject. So essentially, this value is always obtained from this one side of critical region. And then if you go to a table, you can find that chi-square in this case equal the critical value equals 3.8. So that means if your observed test statistic is higher or it's bigger than 3.8, you reject the null hypothesis. Otherwise, you do not reject. And here we observe 0.75, so very naturally we fail to reject the null hypothesis, and we conclude that we do not have sufficient evidence to see that the proportions are different. And what essentially that means, or scientifically that means that we do not have evidence to see female has a different hand preference compared to males. Or we can see that we do not have evidence to see that gender is dependent, or hand preference is dependent on gender. Or you can also see that from this data, we conclude that hand preference is independent of gender. So all those ways are essentially telling you that the proportion of left-hand side is the same between gender and between females and males. So this is what we have talked about 2x2 table. And remember, I actually forgot one thing right here is when we talk about chi-square test, there is always this parameter called degrees freedom. So in this situation for chi-square test, how do you calculate degrees freedom? So degrees freedom in this case for chi-square test is number of column minus 1 multiplied by the number of rows minus 1. So it essentially is if you have k column and if you have j rows in for the two variable, your degrees freedom is k minus 1 multiplied by j minus 1. So For a 2 by 2 table, that gives you the degrees freedom equals to 1 because it's 2 minus 1 multiplied by 2 minus 1. So for 2 by 2 table, when you use a chi-square test, you compare to a chi-square distribution with 1 degree freedom. In the next section, we want to see that it's not only you can use chi-square test for 2 by 2 table, you can also use that for more general case where you have R rows and C columns. So essentially, if you have 2 categorical data and each categorical data has more than 2 categories, you can still use a chi-square test, and the hypothesis is all the same. Under the null, it essentially means that the 2 categorical variables are independent. You can also see that there is no association between the variables in the column and the variables in the row. And under the alternative hypothesis, it's the opposite. Essentially, you can either see that they are dependent, or you can see that there is association between the row and the column. So that is the hypothesis testing for R multiplied by C table. And to extend to that situation is actually fairly easy because the statistic is all the same. As long as you calculate the expected table and then you compare to that observed table, you get the square distance over the expected frequency, and then you just take the summation over all the cells. So previously we have the summation of 4 cells, and now you just have more than 4 cells. There is one biggest assumption for chi-square test, and that assumption or that check is really to see that for chi-square test, it cannot be used for 2 small counts. So if you have any cell or any combination, and under expected value or under the expected frequency, if that cell has a value less than 1, or if you have more than 1/5 or 20% of your cell that has expected values less than 5, chi-square test is typically not applicable to those situations. Those cutoff, whether it's 1 or 5, is not really like scientifically justified cutoff. It's really just some suggested value. So when you have a situation, you need to keep in mind that for chi-square table, it cannot be like the cell count or the frequency under the expectation is too rare. And so when in that general case, how do you calculate the expected cell frequencies? So this is actually fairly, you can generate that the 2 by 2 table in a fairly general way that the expected frequency you can calculate by the row total multiplied by column total over the grand total, or the overall sample size, and that gives you the expected cell frequency. Okay, so let's use an example to illustrate this. So going back to our previous example, when we have the different 4 classes, and then when we have 3 different meal plans. So we are testing that whether students in different years have different preference in terms of when they choose a particular meal plan. So that means that we are testing whether rows are independent of the column variable. And here we have a 4 by 3 table. So 4 times 3. So those are the observed counts. So for observed counts, what you can calculate is the total that corresponding to each row and the total corresponding to each column. And you also have a grand total, which is your total sample size. So after you have this, you can actually calculate the expected table. So how do you do that? The simple way is for each of the number right here, let's say for this number, how do you calculate? You use the corresponding, let's say for this one, 10.5, you use the corresponding row total, which is 30 right here. And then you use the corresponding column total, which is 70 right here. You take the product of those two, and then over 200, and that gives you the expected frequency. So this is, and what is the underlying reason for doing that? Is essentially that's the same like what we did like before. Essentially, we are assuming that if under the null hypothesis that the rows and the column are independent, so that means whether you are a fresh student or sophomore or junior or senior, they should have the same proportion to choose this column. So essentially you are using 70, the total, or the 70 over 200, and that gives you the p hat. And then with that p hat, you multiply by 30, which gives you the frequency of the cell. So essentially what you're doing is this number over this number multiplied by this number. So that means the corresponding column total multiplied by the corresponding row total over the total sample size. So you do that for each of the cell, and then you get this number, this frequency table, which is the expected frequency table. And then the next step is fairly similar to before, is you take the square distance of each corresponding cell between the observed and expected. After you take the square distance, you divide that over the expected cell counts, and then you do that for each cell, and then you take the summation. The summation in this case is a summation of 12 numbers because you have 12 number of total cells. So here you have the chi-square right here, and you have 12 summations. And after you do that, you got chi-square, which is equals 0.7. Yes?
So in the assumptions, you said that you couldn't have a cell less than 1 or more than 1/5 of the cells less than 5. If that were the case, could you normalize all of your cells?
So that means you artificially increase your sample size, right?
Yes.
That is, I would say that is never a valid way to do, because that would inflate your significance or decrease your p-value. Because essentially here, you have 200, that is your total sample. If you mean by normalize, you let's say multiply by 5, and then although every cell is bigger than 1, but essentially what you're doing is you're cheating, because you only get 200 samples, but you pretend that you got 1,000 samples in that situation, right? And this is artificially inflate your significance, because you're making the assumption or the implicit assumption that the 800 samples that you imputed are exactly the same with the 200 samples that you observed, which is not the case, right? So essentially that is not a good choice to do. Yeah. So we get this chi-square, which is 0.7. And then for this one, what do we compare to? We still compare to a chi-square distribution, but in this case, the degrees freedom is no longer 2. It's no longer 1, because here you calculate the degrees freedom by the number of rows subtract 1 multiplied by the number of columns subtract 1. So it's 4 minus 1 multiplied by 3 minus 1. So you got 6 degrees freedom. So here you need to compare to a chi-square distribution with 6 degrees freedom. And from a chi-square table, we can get that that number is 12.59. And at alpha equals 0.05. So very obviously, we fail to reject the null hypothesis and conclude that for the students in different class, they actually have the same proportion to choose different meals. Or you can conclude that the different years of the student or the class of the students have no association with their meal plan choice. So here it's just a little bit more details that we observe 0.7 and the critical value or the critical region is bigger than 12, so you fail to reject the null hypothesis. So that's all about chi-square test. Essentially, remember that chi-square test is a test that allows you to test the independence or the association, or you can see the dependence between two categorical data. Each categorical data doesn't have to have two categories. It can be as many categories as they have. And then essentially, a chi-square test is used to test whether the first variable is independent from the second variable. And the rationale of chi-square test is under the null, if they are independent, you can calculate a frequency table that expected under the null. And then you compare the squared distance between the observed table and the expected table. If it's too big, then you have evidence to reject. And conclude that they are associated. If the difference is not that big, then you fail to reject, and you conclude that this is probably, the null hypothesis is probably correct, that there's no association between the two variables. And the reference distribution for chi-square is a chi-square distribution with k-1 multiplied by j-1. So the number of categories in your rows and in your column, each one subtract by 1 and then take the product. And the application for chi-square test is depending on that you have sufficient number of observations or expectations in each of the cells. If you have very unbalanced design, or if you have very small sample size, that the expected frequency of any cell is less than 1, or a large proportion of the cells with expected frequency less than 5, in that case, chi-square distribution probably does not work. So the next section we want to introduce is, what if that is the case? What if you have a smaller sample size, or what if you have very unbalanced distribution? The alternative to chi-square test is called Fisher exact test. And now you probably, it's clear that for Fisher exact test, what is a scenario that you should consider? It essentially is a scenario that if your grand total is too small, so that means when your grand total is too small, that your expected frequency for some of the cells or one cell would be very small. So in that situation, you might not meet the criterion for chi-square test. This is one scenario. Another possible scenario is if the distribution is so unbalanced, which means that although your grand total sample size is not that small, however, the proportion of one particular cell or more than one particular cell is so small, the expected proportion is so small. So when you do that, the expected count is also small. So in that way, the distribution is very unbalanced across different cells. In that way, you might also fail to meet the criterion of a chi-square test. So this is an example that chi-square test probably doesn't work, and we have to use the alternative test, which is Fisher's exact test. So here we have two variables. The first variable is their diet style, whether it's a low salt or it's a high salt. And then the second variable is a patient's cause of death. And so we categorize those into two cause of death. And one is cardiovascular and the other one is non-cardiovascular. And the question is, we want to see that for the samples that we have, is it possible that the cardiovascular disease, they have those deaths are particularly attributable or associated with their diet style? So essentially, we're testing whether the rows are independent of the columns. So the hypothesis is the same, exactly the same as before. Essentially, we're saying that for the high salt, for people that choose high salt, whether the proportion that they die of cardiovascular disease or die of non-cardiovascular disease, that proportion is the same with the people who has low salt diet choice. Or you can see the other way, that for the people who died of cardiovascular disease, whether the proportion of their high salt is the same with the proportion of their low salt. So this is the setup, and because here we have, the problem here is not that we have a very small sample size. The total sample size is not that small. We have 6-day sample. However, the problem here is the high salt diet category is a very strict category that you have to consume a very high threshold of salt to be able to categorize as a high salt category. So among the 6-day individuals that we sampled in total, there are only 7 of those that fall into that high salt category. So essentially, this is a very rare lifestyle. It's not that everyone is consuming so much salt every day. So we have 7 here, which is the total. And among the 7, we have 2 people that died of non-cardiovascular disease, and 5 of those died of cardiovascular disease. And then in the other 53 that into the low salt category, the number is 23 versus 30. Okay, so if you just look at the number, essentially what you'll see is, first of all, the number here, each cell for the high salt, whether it's non-cardiovascular or cardiovascular, is very small. And second of all, you can see that it seems that you do have some evidence to see that the high salt dietary have a higher likelihood that the people that will die out of cardiovascular, because you have, like here, more than 2 times or more than double of the number who died of cardiovascular compared to this column that is roughly the same. So here, this is intuition that when you look at the table, what should you do? First of all, you probably cannot use a chi-square because the number of cells is so small for some of the cells. And the second of all, it seems like you have weak evidence, but remember, because of this number is so small, so that is always associated with higher variance as well. So now the question is really, do you have enough evidence that the high salt people do have a higher chance or higher probability that they die of cardiovascular disease? So how do you perform a Fisher's exact test? Fisher's exact test, although it's testing the same hypothesis, is actually using very different rationale compared to a chi-square test. Fisher exact test essentially tells you perform on conditional probability. It basically tells you under the null hypothesis, if the high salt individual has the same proportion of cardiovascular or non-cardiovascular compared to the low salt individual, what should you expect given you have this 25 and 35 and given you have 7 and 53, those margin fixed? So essentially, conceptually, given you have those numbers fixed, if you assume that the rows and the columns are independent, you can see that this is my number that I observed. What I can see is I can de novo or I can just brute force calculate the p-values, because the p-values is a probability that you observe this number or more extreme. So chi-square test, if you think about it, it's really doing this way. Like here, you have 2 and 5, and you have 23 and 30. And you have here, which is 25 and 35. And then you have 7 and 53. And your total is 60. So this is your observed. So chi-square test is really when you fix those 4 numbers, what is the more extreme situation that you can observe, that you can expect if the alternative hypothesis is true? So if you think about it, that means you need to enumerate all the possible scenarios. So what does that mean? Here you have 7 in total, and they are distributed as 5 and 2. So if you got 6 and 1, you fix this number unchanged. But now you got 6 and 1, which essentially means that among those 7 high salt diet people, now you have not only a 2 times ratio, a 2 somewhat ratio, you have a 6 times ratio. So this is even more extreme, or gives you more evidence towards the alternative hypothesis. So this is one scenario. Or you could have other scenario that, that the distribution is even more, which is 7 and 0. So essentially, Fisher exact test allows you to enumerate all the possible scenarios or all the possible observations that it's even more extreme than your observation. Okay, so after you enumerate all the possible scenarios, what is the p-value? If you calculate under the null hypothesis, what is the p-value? What is the probability to observe this table? Let's see, you got this. And then under the null hypothesis, what is the probability to observe this table? And then you have this observed, which is, so let's say this is P1 under the null. This is P2 under the null. This is P observed under the null. Let's see. Those are all my enumerations. Those are all the situations that is more extreme supporting the alternative hypothesis. So in that case, what is the definition of p-value? The p-value is under the null hypothesis, what is the probability that you observe the observed statistic or more extreme? So what exactly does that mean in this situation? It means if you only have those 3 scenarios, one is observed, and then the other 2 is more extreme. The p-value is exactly equal to the summation of the 3 scenarios, the probability of the 3 scenarios. So that is the p-value of Fisher exact. So now you understand the name. It really gives you exact p-value. That is because here you're not using any central limit theorem. You're not using any asymptotic distribution. You're just you just calculate the p-value by the definition of p-value itself. And now you also understand why the Fisher exact test is especially suitable or efficient for small counts. Because only if you have 7 here, a very small number here, then you have more accuracy or more efficiency to enumerate all possible situations. If you have 17 here, let's see, this is 12 and this is 5, then you probably need to have a lot of scenarios that you need to enumerate, which is really tedious. So this name really gives you the rationale of Fisher exact test. You do not depend on any asymptotic theory or central limit theorem. You just, by the definition of p-value, you just enumerate all the possible cases that is even more extreme than your observations, and you just take the summation of your observed probability plus the more extreme case. And then the only problem is how do you calculate this proportion? And that is under the null by binomial distribution, the PDF. So for this course, or most importantly, in your research life, you will not need to learn how do you enumerate all those scenarios. You'll not need to learn how do you calculate each probability. All you need to know is Fisher exact test, what is the rationale, and what it's used for. It's used for testing independence between categorical data, and also it's used for particularly when you have very small counts or small sample size. I put some R code here because in R, to perform Fisher exact test is really fairly simple. You give it a table input right here, and then you use this Fisher.test, and you give this input right here, and then you get a p-value of 0.68. And look at here that the alternative hypothesis is a true odds ratio, or we didn't introduce odds ratio in this course, but essentially it means that the rows and the columns are not independent. That's the alternative hypothesis. So this is how you perform a Fisher exact test in R. I hope that you also learned that in Python, how do you do that. But essentially, for Fisher exact test, for this course, all you need to know is when do you want to use the Fisher exact test, and then what is it based on, understand what it is based on, and then how do you implement that in the statistical software.
So where does the 95% confidence interval?
It's a good question. So this is the confidence interval, or the 95 confidence interval for the odds ratio. Yes. And it calculated also use this method. Do you understand what is the odds ratio? we haven't introduced odds ratio at all in this course, because odds ratio is a frequently used concept in statistics, but not really in bioinformatics. Stuart can correct me if I'm wrong, but essentially, odds ratio is a ratio of odds, and odds is defined by p over 1 minus p. So in a 2x2 table, odds ratio can be very simply calculated by the ratio of the cross product. So 2 times 30 over the product of 5 times 23. Okay, so we have essentially in this course, we talked about what if you have 2 categorical data and you want to test whether they are independent or not. And the test that you should use, the way that you should present your data is called contingency table. And then the test that you can use is either a chi-square test or a Fisher-exact test, depending on what is the sample size or what is the distribution of the total sample size across different cells. Okay, so that's all for categorical data. And so we have about 30 minutes left. I would like to move on to the next lecture, which is non-parametric test. There's an adjustment of the order of the of our lecture because I would like to talk about non-parametric test first because we can finish most of that today. And then the next two lectures, we are going to talk about regression because regression is a very important concept. And in most of the statistical course, we spend a lot of time on regression. However, because this course, we want to give you an overall, introduction of biostatistics, so we only left one lecture allocated to regression. So I'm trying to rush a little bit of the previous lecture and then give you some more time to learn about regression. So this probably hasn't been posted online, but it will be after today's lecture. And today's lecture is really about non-parametric methods. All the rest of the lecture is about non-parametric methods. And so non-parametric method here is actually, in general, this term is a very big terminology. And it's used for a lot of statistic tests that falls under this category. It essentially means that when anyone is talking about non-parametric or non-parametric test or non-parametric inference, it essentially in statistics, it means distribution free, which means the test should be applicable to the data from the population coming from any distribution. It doesn't have to be a normal distribution. It doesn't have to be a binomial distribution or chi-square. It has, for non-parametric tests, it really needs to be distribution free. So that is a general definition of non-parametric statistic. And for this course, what we are going to talk about is what are the non-parametric statistical methods or tests that can use to complement what we learned before for those t-tests or ANOVA or something like that, that can allow you to do some inference that where the previous scenario or the previous test wasn't appropriate for. Okay. So non-parametric test, like we said, is distribution free. So non-parametric test or non-parametric inference, typically, it does not depend on any knowledge of the PDF function or the underlying probability function. And on the other hand, you know that what we have talked before until today, everything we talk about when you have a test statistic, you compare to some reference distribution and all those kind of things. We also talk about whether it's continuous, whether you should use central limit theorem. All those falling into the category of the opposite of non-parametric test, which is called the parametric methods. So today, or the rest of today, is the only part that we talk about non-parametric. And all the rest of this lecture in statistics is parametric methods. So what are the nice things or what are the characteristics about non-parametric method? First of all, it's distribution free. So that means it doesn't require normality. Second of all, where do you typically consider that you should use a non-parametric test? There are two scenarios that is the most common. The first one is when you have very small sample size. Because remember, most of the time we talk about comparing means of two distribution. We require that the sample size needs to be big or the data is normal distributed. So if neither of those is satisfied, what should you do? And that is the situation that you can consider to use alternatively non-parametric test. Another thing which is sort of aligned with the distribution assumption, but it's actually a very typical scenario, is when you have data that have very obvious outlier present. So essentially, if your data has a very obvious couple outliers, that, of course, it will make your total distribution non-normal. However, those outliers could essentially impact your test statistic. So your hypothesis testing is quite driven by those outliers. So especially for t-test, it's quite prone to the presence of outliers. So in that situation, if you do not want to give too much weight or too much influence to the outliers, and you want your test to be, in statistical we call robust, sometimes you can consider a non-parametric test. So for that, it doesn't have to be small sample size. The sample size can be big, but if you do not want your decision to be completely driven by the outliers, that is a scenario that you can also consider non-parametric methods. Okay, for non-parametric methods, actually, when you talk about distribution free, there are two types of introductory non-parametric methods that is most widely introduced or most widely used. The first method is called permutation-based method. So permutation-based method, you probably have heard that quite often, especially in bioinformatics. A lot of times you use a permutation-based method. And the second method is called rank-based test. So rank-based test is the main theme that we're going to introduce, because rank-based essentially, after we introduce today, you will see why it is less influenced by outlier or why it is less influenced by non-normal distribution. So when we talk about rank-based, the first thing we need to tell you is what is rank. So rank is actually a fairly common concept that a lot of people, that I believe you have all used in your research. Rank is essentially if you order the observations, and then the rank of the observation is the relative position of the observation's magnitude compared to the rest of the sample. So that is rank. And in statistics, you need to know that rank is essentially distribution free. It has specific distributions that particularly apply to rank. But here what we mean by distribution free is no matter the observation coming from what distribution, whether it's normal distribution or Poisson distribution or any type of distribution, once you take the rank, the distribution of the rank does not depend on the original distribution. So this is especially what we mean by distribution free of the rank. Essentially, the rank has a unique language that is independent from where the original data comes from, what distribution it comes from. And sometimes a practical problem is when you have the ties in your observation, how do you assign a rank to the tide value? There are different methods, but here a very popular method, and we are going to talk today, is you can compute the average of the ranks that if they are tied and assign to average. The other method you can also use. So here we give you an example of what is rank here. So in the second row here, we have the observations. It doesn't matter what distribution it comes from. And then you can essentially rank them. So you can rank them from the smallest to the biggest. And here, these are their positions, the ranked positions. And because here you see there are 2 ties right here and 3 ties right here. So in this course, you can handle that by taking the position of the ties and take the average and assign that as rank. If you talk about continuous distribution, actually, ties should not be there, because for continuous distribution, you can always go more precise and avoid ties. So, you take the position of the tied observations, and then you take the average, and you assign that as a rank. The average of the tied observation. For example, if you have 0.7 and 0.7, and they are ordered, like, see, 3 and 4, and then you take the average of 3 and 4, that gives you 3.5. Yeah, like 3.1, they are ordered like 7, 8, 9, and the average would be 8, and you give it an 8. So in that way, you essentially you assure that the tied observation has the same rank. Okay, so the specific 2 tests are the 2 alternative tests that we're going to talk about, in addition that parallel to the previous test that we talked, is called Wilcoxon Sand Rank Test and Wilcoxon Rank Sum Test. And they have specific usage. The first one, the Wilcoxon Sand Rank Test, is used for one sample or paired samples. So essentially, it's one sample or one population hypothesis testing, or when you have 2 populations, however, they are paired or correlated. And the next one, Wilcoxon Rank Sum Test, they are used to compare the 2 populations if they come from 2 independent populations. And again, what is it good for? It's good for small n. It's good for deviation from normality, those we introduced before. It's also good for ordinal data. So what do we mean by ordinal data? Ordinal data means they're not continuous. We talked about this before. Essentially, you can order those, but you cannot give it a particular value. For example, before I came here, I was doing some consulting with some oncologists. They have a clinical trial, and what they want to do is they evaluate their outcome by complete responder, partial responder, and non-responder. So they have the 3 categories, which they do not really know what value, or they actually don't think that assigning 1, 2, 3 or 2, 3, 4 to any of the category is valid, because those are too arbitrary. However, they know the order. They know that the complete responder respond better than partial responder, and then they respond better than the non-responder. So in that way, they want to see whether the 2 arms, the 2 population, the control arm and the treatment arm, have the same response rate. So that is a very typical scenario for if your outcome is ordinal outcome, and then you are comparing the 2 populations. So in that way, suppose the data is let's see, you have 3 CR, 3 complete responder, and then have 4 partial responder, and then have 2 non-responder. What do you do? How do you assign the rank? Essentially, you got NP, NP, CPR, 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 actually CRP, CRP, and CR, CR, and CR. So that is all the data. 2 non-responder and 4 partial responder, and then 3 complete responder. So we know that those are tied, and we know those are better, and those are tied, and those are better. right? So this is essentially the data. It's ordinal, it's ranked, but it doesn't have actual value. So what you can do is you can actually validly obtain the rank of those data. What you do, you give it a position. And then you can give it a rank. So thus too, the rank would be, according to our previous method, we can give it a rank, which is the average of 1 and 2. And this one is 3, 4, and 5, 6. So the average would be 4.5. And this one, the rank would be 8. The average rank would be 8. So you can give it an 8. So this is the observed outcome, and this would be the rank. So remember, although the outcome is ordinal, you can't put actual number on that, but the rank, you can actually put actual numbers on that, and that's actually valid. So this is what we call the ordinal outcome. Essentially, it means that outcome that is categorical. However, you can sort those. There are some orders of that categorical outcome, which is called ordinal outcome. Okay, so when you have small n ordinal outcome or data with outliers, non-parametric tests, especially for the two tests that we are going to introduce today, would be very good alternative for you to consider. Okay, so this really tells you what is the ordinal data compared to like what is continuous data. So for ordinal data, essentially data can be ordered but do not have specific value. For example, you have high school, college, postgraduate degree. Or you can have, so it's convenient to use rank instead of any numerical value. Okay, so we'll move on to the first test, which is called Wilcoxon signed rank test. It's used for one sample or paired samples. So those are the different steps. Before we go there, we still follow the same recipe that we introduced anti-hypothesis testing. So first of all, Wilcoxon signed rank test, what is used for? It is used for comparing the two populations which are correlated, or it is used for comparing the one population to a specific value that you predetermined. But here, there's one difference between here and what we talked about before, like one sample t-test or two sample t-test of paired data. Here, for any rank test, especially for rank-based test, you're talking about comparing the two populations. But here, you're not talking about comparing the means of the two populations. Essentially, you're talking about comparing the median of the two populations. The basic concept is still the same. You're comparing whether these two populations have the same location. They have the same center location. Previously, because you can assume it's normal distribution, or you can use central limit theorem, so it's pretty much a bell shape, and then the mean is your central location. Now, because the data can be any distribution, so essentially, if this is like one population, and then this is the other population, and you're comparing between those two distributions, essentially, you're comparing you're comparing the median of this two distribution, or you can see the center of the distribution location of the two distribution. Or sometimes people say whether there is a shift of location of the two distribution. So remember, any of the Wilcoxon rank-based tests, those are based on comparing the median. Although conceptually, you are essentially comparing the central location of two populations. And then, so after we know that what it's used for, the next thing that we need to know is how do you construct a test statistic? And for Wilcoxon signed rank test, a test statistic is constructed this way. So suppose we put that in an example that we have paired tall and short individuals, and we are interested that whether there is salary discrimination against short. So here we have male samples. So essentially the sampling that we get is we got one tall guy and then we got a paired short guy. They have similar position, they have similar experience, and we ask for their salary. And the data that we get, or the data that we present, is in this way. Suppose X right here stands for the salary of the short samples or the short males in our sample. We got 10 of those. 1, 2, 3, 4, 5, and 10. And then Y, which is the salary of the tall individuals that we get. And remember, they are all paired by experience and by their occupation. So here we have n equals to 10, which is probably a little bit too small in terms of using central limit theorem. So here, let's see, how do we use a Wilcoxon signed rank test to test whether the salary is the same for short and tall individuals? So here, how do you do that, or how do you construct a signed statistic? So the first thing again, which is similar to before, you still get a D, which is the paired difference. You still calculate D equals X minus Y. So short minus tall. Okay, so this is the same. Previously, you calculate this D and then you perform a one sample t-test on the D, on the difference. Now what you do, after you calculate this D, the next step is you get the absolute value of the difference. Essentially you ignore all the sign here, whether it's positive or negative. You ignore all the sign here and you get the unsigned difference. The next thing you do is you get the rank of the unsigned difference. So you got 1, the smallest one is 0.3, and then the next smallest one is 1. So you essentially get the rank of those. If you have tie, it's the same way how you calculate the average. Okay, so the next thing you do is get the rank of the unsigned difference. The last thing that you do is you get the signed rank, which is how do you get that is you use this rank and you assign a sign here based on the actual sign of the difference. So here 0.3 is a negative one in the actual difference, so you get a negative 1 here. And here you get a negative 2 here. So this is how the name comes from. You get a rank, but the rank is signed rank, and the sign is assigned according to the actual difference. Okay, so after that, it's actually fairly simple to construct a test statistic, which is you can do that by 2 ways. One way is to get the summation of the positive rank. So you take only the positive ranks and you take the summation. And then alternative way is you get the summation of the negative ranks. you only need to get one of those because the p-value that would be the same no matter which one you're looking at. So this is probably like quite look like a cooking book that you are doing step by step without really thinking about why you do this. I can give you a little bit of explanation of why you do this. Essentially, the idea is if the null hypothesis is correct, that means if you take the difference, that means the positive difference and the negative difference, they should be roughly the same or balanced, right? So if your difference is like you have half of the individual that is positive and half of the pairs are negative, and especially if you rank them, you see that the positive side of the total rank is similar to the negative side of the total rank. In that way, you have more evidence to believe that there's no difference between the short and the tall individual salary. So essentially, if this is the difference, let's see, if this is 0, and you got each pair's difference, and they are distributed on the, like this way. This is 0, they have some of the negative difference and some of the positive difference. If you believe that the two group salary should be the same, so that essentially means that you're randomly selecting balancely between negative side and positive side, that they should be evenly distributed, the positive and negative, right? So that means if you look at this is all rank. So if I randomly select those are the positive and the rest are the negative. So if you take the summation, the positive rank summation should be roughly the same with the negative rank summation. So essentially it tells you that these two rank should be similar if the null hypothesis is correct. However, it should have a huge difference if the alternative hypothesis is correct. Let's see, x tends to be much higher than y. So that means your d, which is x minus y, most of the d should be positive. So you should have a much higher or bigger positive sign, positive rank, summation of rank. So this is the underlying intuition. So now essentially you know that you need to compare this W, whether how balanced between these two W. And then the next question is, how do you know whether it's balanced or not? And so in this slide it tells you W1 equals the positive rank, the summation of positive rank, and W2 equals the summation of negative rank. And then how do you compare, or what is a reference distribution? That is called the Wilcoxon distribution. Wilcoxon distribution essentially tells you whether they are too large or too small. So you can use table 11 in the textbook to get the p-value. The p-value is equals to 2 times multiplied by this proportion, which you can obtain from that table. Most practically, when you use Wilcoxon sand rank test, you probably will not refer to any of the tables. You probably will just do that from a statistical software. So in R, what we teach to use is this way. So you have, let's say you have X and you have Y, and X equals to the previous 10 numbers that we show on this table, and Y equals to the second 10 numbers. In R, what you do is you use Wilcox.test, X, the first sample, and the second sample. Because here it's paired design, so you put paired equals to true here. So you can see R automatically use a test which is called Wilcoxon signed rank test. It calculates a statistic, and then according to that statistic, it gives you a p-value. And you can see that the alternative hypothesis now is, it doesn't talk about mean anymore. It talks about true location shift. Under the null, the location shift is 0. Essentially, the two populations has the same location, central location. Under the alternative, it means that the two central location position is different. There is a shift. So, I believe most of you do not have textbooks, and even if you do, I believe most of you will not, go to calculate this by hand and then go to a textbook and to get the p-value. So essentially, you need to know how to implement that either in Python or in R to get this. But conceptually, what is most important is to know that when do you use Wilcoxon signed rank test. That is when you have paired sample of you have one population, too small of sample size, or a lot of outliers. And another situation is if you have ordinal data that you can only rank, but you cannot get actual value. Yes?
So what is the basis for accepting or rejecting your null hypothesis?
What is the
basis which you're accepting or rejecting the null?
It essentially means that, if you observe like this two sum, when one is positive rank and the other is negative rank, is this two sum rank is too unbalanced, that you have one super big and one super small, then you tend to reject.
But what's the critical region? Like what's the cutoff?
That you need to get from the table.
Okay.
Okay, so let's see how much time I have left. So I have almost used up all my time, and let's see. The next part is called Wilcoxon rank sum test. So this test actually is even more often used compared to the previous test, and this one is used to test the shift in location when you're comparing two independent populations. And it's also used for those situations where you have small n ordinal data or data with outliers. And here I told you that it's comparing two medians. Okay, and I think we can stop here, and the next lecture will tell you how exactly you calculate the test statistic for Wilcoxon rank sum test and how do you get a p-value. Again, we will not tell you, what is the underlying distribution and all those details, but essentially you understand the rationale of Wilcoxon rank sum test. So those are for the next lecture. Just to summarize what we have learned today is we learned two rank-based tests, and both of those is called non-parametric test. That is because those tests can be used for data that coming from any distribution. And both of those are based on rank. So for any test that is based on rank, essentially you're not comparing the mean of your population. You're comparing, because rank really gives you the position. So whenever you use a rank-based test, it's comparing median, or you can conceptually see it's comparing the central location of the two populations. And then it is very good for data that doesn't follow a normal distribution or small sample size or ordinal data. And most likely, it is very flexible, that it allows you to use when the sample size is very small, or when you have very strong outlier presence. The sacrifice that you use for non-parametric test or rank-based test compared to a parametric test or two sample t-test or one sample t-test, the sacrifice you use is if for scenarios that both types of tests are appropriate, However, you choose to use a non-parametric test. The price that you pay is you don't have as much power as you do for the two-sample t-test or parametric test. Remember what we call by power. Power means if the alternative hypothesis is true, what is the likelihood or what is the probability that you'd reject your null hypothesis? So in other words, parametric test or t-test give you higher probability to reject the null hypothesis if the alternative hypothesis is true. However, in that situation, when it's appropriate to use parametric test, but you choose to use non-parametric test, the price you pay is your likelihood to reject the null, even when the alternative is true, is lower. You decrease that probability. So you have less power for non-parametric test. This is quite understandable because if you think about it, you observe, let's say you observe quite dramatic difference for the tall guys compared to the short guys. The salary difference is so much higher than zero, much bigger than zero. But when you take rank, you completely ignore the magnitude of the difference, the salary difference. You just get the rank. So in that way, you actually lose a lot of information of the data that you have. And you use a surrogate or some suboptimal statistic to perform your hypothesis testing. So in that words, you are losing power to reject the null hypothesis. However, the advantage of, first of all, it's more flexible. And the second advantage is it's more robust. Because suppose in your sample, you happen to get one guy is working in a startup and get a big stock option, and the short guy doesn't have that choice. So that gives you like $1 million difference. So in that way, if you use a two-sample t-test, you obviously got influenced by that one pair of sample. However, if you use Wilcoxon test, it doesn't really matter because for that, it still gives you just one rank, which is reasonable. So that is the pros and cons. The bad thing is you lose power. The good thing is you are safer and you are more robust. So it's really your choice to choose between the two types of tests. And here we only gave you several guidelines that, for sample size or for ordinal data that you have no way to use t-test, or for data with outliers. But most likely, in your real life, you need to consider more carefully which type of test you want to use. Okay, that's it. For the next lecture, we will start by telling you the details of Wilcoxon's rank sum test, and then we will go to regression.